But first, let me just pose a question, just to gauge uh, where people are at in this class. So I'm gonna pose a puzzle, okay? Which is a very old puzzle, but at some point you encounter it either when you are in high school or when you're a grown-up and you need to sort it out. Otherwise, you cannot continue with your life. So the puzzle is very famous. So there's a charge. It's a plus charge. It might be an electron. Sorry, those are negative. So there's a Coulomb field, which you may be familiar with. It decays as 1/r, right? And then, they ask you, okay, what happens in the charge exactly? It's a point particle, so you cannot split it into strings, right? We don't believe in string. Okay, we believe in the string theory, but you cannot decompose a fundamental particle. And you say, well, it's okay. Maybe the force is infinite, but it's coming from all directions, so there's nowhere that you can break the symmetry into, so it just stays there. That's fine. But then something, maybe some external field, if you want, starts accelerating this charge, right? So you start slightly accelerating it. And what happens with the acceleration? Well, I'm not very good with this drawing, but you will see that the electric field lines start compressing. And you know that implies radiation, right? So there is a radiation field. It's more powerful than the 1/r square of the Coulomb potential. This one goes as 1/r. And so the charge at some point will start filling this 1/r radiation field, right? And so again, now there is a direction, so there is no symmetry. So what happens? Do we have infinite force on the particle? So that's the puzzle, right? And at some point, you learn how to deal with it. But this is sort of the imprint of what I'm going to talk about just tomorrow, which is the notion of self-force, right? And we're going to learn, hopefully, how to deal with self-force today at the end of the lecture. But I'll let you think of that puzzle, and hopefully, by the end of the lecture, we can answer it. Okay, so let me just recap. I'm just going to recap this Schwinger-Keldysh contour for two reasons. So one reason is we're going to use it in what's next. And the other reason is that I messed up the notation, so I want to fix it. And I want to do it properly so that I can hopefully continue. So I'm going to call the upper branch, I'm going to call plus. This might not be the standard one. I was calling it 2 or 1 yesterday, but I wanted to just be a little more consistent. And then what we're going to do is we're going to analyze different locations just with two fields, right? So we're going to understand just two fields, let's say phi 1 and phi 2, right? So we will have two copies of those fields as we discussed, and then they can be in the plus or in the minus branch, right? Okay, so the first thing, maybe just to set up the stage, if both fields are in the plus branch, sorry, I already messed up again. If both fields are in the plus branch, then what happens? Then what you get is a time order correlation function. Okay? This is just because we don't really distinguish the lower branch. There is an epsilon here. So if there is nothing here, we just take epsilon to 0. Sorry, there's an I epsilon if you want. Okay, so what happens when I have, I hope I do it correctly this time. So imagine time going from minus infinity to infinity, and then coming back, right? So in this picture, okay. In this picture, which I kind of, sorry guys. Yeah. In this picture, I'm going to compute something that looks like phi1 minus, phi2 minus, plus phi2 plus. Okay, so let's just discuss the case in which, so I have only phi1 here. I don't have the phi1 plus. And I imagine that I have x0, which is going to be the label of this time, greater than y0, which is going to be the label of this time. So in the case where I look at this term, right, both are in the plus, in the minus branch, then what I get phi2 first, and then I get phi1 later. But in the case where phi2 is in the plus branch, I get, in the time ordering, which is my path integral along the contour, I get phi1 first, and I get phi2. Thank God it worked out. OK. And I get phi2 later, right? So because I'm integrating from minus infinity to infinity and then back. So if I imagine the second term, I only have these two. I find phi1 first, and I put that guy to the right of my correlation function. OK? And that's just the commutator, right? So it's phi1, phi2, right? The commutation of, and this is true only when x0 is to the right, because if x0 was to the left, then in both situations you would encounter, so if x0 was here, right, so if phi1 was here, in both situations you would encounter phi2 in the future, so these terms would cancel, right? Okay. And so what that means is that this calculation gives me a step function x0 minus y0, phi1, phi2. Okay, why is this important? Well, because it's causal, right? So we have a correlation function that vanishes in the future. It's always reading of what's going on in the past, and it's a response. It's a response. I didn't explain it very carefully yesterday because no one asked, but it's a response because if I had some interaction Hamiltonian involving my field, say phi2, I'm going to do it very schematically, but you can imagine adding your interaction with a field phi2. This will shift your field phi1 by a term that has to do with the commutation. Yes, because it's Hamiltonian, you commute phi1 with your interaction Hamiltonian, right? So this would be a response of having this operator, right? So that's why these commutators are important. This is what we compute when we solve the wave equation, and that's what we are going to do in a second. There is another option, which is let's do phi2 minus with phi1 minus and phi1 plus. So anyone has any guess what's this correlation function called? Right, correct. So this one I'm going to call the retarded correlation function, and this one I'm going to call the advanced correlation function, right? And so you just notice that here all I'm doing is I'm changing 1 and 2, right? So to change 1 and 2, I get a minus from the commutator, and I get, I just exchange this, so I can get the opposite sign with the same commutator. Okay. And well, I hope you guys don't know what this is, because if you know, then I'm just going to bore you the whole lecture. But this is the most interesting object in this lecture. And you can imagine what happens when you subtract this one, right? You take the step function minus the step function of the negative argument, and you get 1. So it's a commutator. Okay. And we're gonna call this the radiative propagator. Okay. And we're gonna discuss what happens with the radiative propagator. Let me just make one comment about before I jump into this radiative thing. This contour actually came from some discussion of finite temperature. So actually, the contour doesn't really end in minus infinity. It ends in minus infinity plus I infinity. So actually, in the regions where so sometimes we have finite temperature, which means that there is an identification of the imaginary direction. So we have a cycle here. And then it's actually a contour, a closed contour. And then you can prove that when, and this is going to be important maybe if you do cosmology or you do some primordial gravitational waves. When the contour is like this, I can prove that I can, so in the second term, right, so I have phi2 here and phi1 here, I can prove that I can displace phi2 around this closed cycle and put it back in the first branch by the action of Hamiltonian. So this is the action of a Hamiltonian in the time direction. And what that means is that in some cases, in the cases where I can do this, then the two terms are actually the same. So the first term has to do with this, right? And the second term has to do with opposite branches. But if I can do this rotation, then the two terms will be the same up to a phase, where the phase is essentially this Hamiltonian. So let me just write that somewhere here. This is going to be, just for your entertainment, this is going to be probably, I'm going to mess up one factor, but the two terms here are equal. So there is a factor of beta omega minus 1 times the so-called Whitman function. And what the Whitman function is just putting one after the other, irrespective of the time. And so we can do the same for the time order correlation. So there is essentially one single observable at finite beta in some situations. And this is interesting because we think of these two-point functions as different objects. One is causal, and the other one is time ordered. But in some cases, there is some analytic continuation. Anyway, that's just a disclaimer. Okay, so let me just go into the radiation problem for 1 second. Maybe I just delete this. Okay, so I told you there is this function called the radiation kernel. So let me just analyze it in a toy model. So this will be a toy model. We are going to do a scalar, even as simple as possible. It's going to be in flat space. Okay, so it's going to be in flat space. Okay. In this toy model, I have a massless scalar that has a source. I'm going to omit the coupling. I'm just going to call the source J. And Obviously, what I'm really thinking on is something that has to do with gravity, right? So there is some graviton at some point, some projection, and then there is something like looks like 16 phi g t mu nu, all that stuff, right? But this is kind of the simplest version. It saves me a lot of notation. Okay, so what are the solutions of this? Okay, so I'm just reviewing what happens in the field theory. We do our retarded propagator, which is exactly this propagator I wrote here. Has this. Let me just do it very implicitly for now. I'm just going to write, because this is not as important as what I want to say. Right, and then you have this solution is a retarded solution. When you choose this solution, and obviously you know what happens with this thing, right? So box of G is a delta function, right? When you choose this solution, what you're doing is you're fixing your boundary. Okay, this is what it means. You're fixing this solution. You know that you can add homogeneous solutions, but you're fixing the boundary conditions such that because this is retarded, it only cares about what's going on in the past. So that means that you are reading off what's going on somewhere along your light cone. If you go all the way to null infinity, and you assume there is no sources there, and if the sources are compact, then the field vanishes because there is no advanced component, right? So this just means that I'm choosing my boundary conditions such that at null infinity, the field vanishes. Okay, and so analogously, you can imagine doing the same for the advanced. I'm not even going to write it. Okay. Okay. So here's what Dirac famously observed. I mean, I simplified the argument and the notation, but the idea is very simple. It's just the fact that this solves this equation, and so does this, right? And the question is, what happens? So what's the difference between the two? So the difference, phi radiative, let's call it radiative, phi r minus phi a, is a solution of the homogeneous equation, right? And so you may think it's trivial, but again, it actually has to do with what's going on in the boundary, right? So there is all kinds of solutions depending on what my boundary conditions are here. And that's obviously a trivial observation. And then the non-trivial part, if you want, which is also very trivial, is the fact that as you go to plus infinity, as you go with the causal solution, right? This is causal solution, to plus infinity. I'm not sure how to denote this, but I'm just going to say limit as y plus infinity of phi retarded is the same as, any clue? It's a radiative solution. Why? Because we have the retarded field equals radiative field plus advanced field, right? But as you move here to plus infinity, you will only care about what's going on in your future. But what's the future of plus infinity? It's just a space like infinity, and hopefully you don't have anyone there. Whatever happened already happened. Everything decayed. There is nothing here. Hopefully. So in that situation, this field actually is very useful. It's the one that's going to construct scattering amplitudes, and is essentially composed of the part of the causal field that we really care about. This will have to do with amplitudes. Okay, I'm going to explain this in a second. Sorry? So for my radiative field? Yes. Uh, I'm not sure I understand. You're asking about the finite temperature case? Oh, yeah, in that case, we expect that phi is defined on the, so really there's no boundary, right? So now I am identifying everything, this is an S1, but there is really no boundary. So that means that this phi can be, well, if you want, there's a branch cut, but the phi can be identified with the upper one up to a translation. Yeah, but there's really no boundary. That's the magic of finite temperature. But that's not our case. Obviously, in our case, the temperature is infinite, right? And so what happens is, beta is infinite. That means temperature is 0. So what happens is that we are opening up this cycle, and now we have these two boundaries, so we cannot continue. So these two objects are really different. And yeah, so this is just a comment on the thermal case. Sorry. Okay, so let me just continue, and let's just try to calculate this retarded green function. I mean, I'll just write the standard formula just so that maybe you're familiar with this situation. It's something that looks like x. Essentially, it has support when this thing is in the light cone. I'm going to write it like this. Yeah. Okay, that's just the fact that it's a retarded function. It has support in the light cone. Okay, that's not a trivial fact. Let me just say that that is actually not true in general. It's not true in higher dimensions, and it's not true in GR. You can get something in your light cone or inside the light cone for causality. But this one is exactly in the light cone. Anyway, now what I'm going to do is I'm going to compute it. Okay, so how do I compute this thing? So I'm going to do Fourier transformations, right? So just going to do the Fourier transform of the retarded green function, right? So I mentioned yesterday what you do is you take k vector and you subtract on the energy component. Here I'm calling x the difference of x minus y. Hopefully you agree or you have seen this formula and you can tell me why it vanishes in the future. Just the fact that you can integrate k0, and depending on whether x0 is positive or negative, then you get 0 or 2 terms. Okay. What is r minus a? Okay, so now we have to subtract this minus its time conjugate. So we say we need to have some way of subtracting. Maybe I'll just do it. So you have something that looks like k0 squared plus 2I epsilon k0 plus epsilon squared, that doesn't matter, minus k squared k0 squared minus 2I epsilon k0. Okay? And the 2 doesn't really matter. Okay, I'm just redefining epsilon. All that matters is that epsilon is positive. And depending what, yeah, so positive or negative give me a different sign. Okay, so what is this? Well, you have to care about the sign of k0. That's all you have to care. And so you get the sign of k0 times delta k squared times the 2 pi's that I'm not going to keep track of, or an I or something. Okay, maybe the I is important. Okay, so now this radiative green function is given by d4k. I'm apologize for all the 2 pi's. I'm really not going to have time to write. OK, this is the last one. And there's a sign of k0. And then delta k squared, so it's on shell. And then e to the ikx, right? And if you imagine, I'm going to even take one step further. If you imagine we're solving for the field, right, the radiative field, this field in x, right, is just going to be the green function in k space multiplied by the current in k space. OK, and the crucial thing that I want to emphasize is that this k0 is here and is a consequence of this retarded effect, right? And we can even make it more explicit if we integrate in k0. Sorry, yeah. If we integrate in k0, we can say this is d3k. There is usually some k here. And then you have e to the I k t e to the I k x j k. So this is j k k minus, there is another solution where I flip the k0 to be the negative. E to the I k t, e to the, sorry, minus e to the I k x j minus k. Okay. Okay. So that's the radiative field. It looks like we have a mode expansion, right, where these j's are our fields at, well, for now they are fields in the Fourier space. But now it comes the homework, or maybe the calculation that I'm too lazy to do, but it's some calculation that at some point you're going to have to do. It doesn't matter if it's now or you already did it or maybe in the future. So, you know, if we are hanging out 10 years from now and then suddenly you find me in a bar or something, you come and tell me, hey, actually, I never had to do this calculation, and you lied to me. Actually, it's completely useless. Now ChatGPT does it. We forgot about this silly solid point. Well, then I say, okay, well, you know, but at the time, you know, when I was young, I had to do it, and I had to get the pi factors right. So there is an 8 pi squared here that I can tell you immediately, and there is an x. And what I'm going to do is I'm going to take the limit of this thing when I take the radius to be very large. Right? So I take phi radiative. And then I want to know what happens with this integral over k. Right? So the integral over k will have 2 components. And sorry, it will have 3 components. So d3k will be omega. So omega squared d omega, sine square theta d theta d phi. Let me just call this the sphere, right? Right. So what's going to happen is, I'm just going to write it here just so that we can save some time. Omega d omega, the sphere. Omega is nothing but the radius of k, right? It's just the magnitude. So I just call it omega, but so it's here. And it's here as the magnitude, so there's only one direction, right? And it's also here, and here I have the direction and omega. And I have the same thing there. I'm not even going to write it. So what's going to happen is that I'm going to take x to be very large, right? X to the radius will be very large. So this thing will start oscillating. And when would it be stationary? Well, when n, the direction of my momentum is aligned with the direction of x, which is the direction of observation, right? So now I'm imagining that, again, I'm looking at it from very, very far using this retarded propagation. So there is some source. And then x is very large, it's almost in non-infinity, and then I take the interval over all momentum in all directions, but it's going to localize. It's going to localize when n is in the direction of x. Okay, and this is like a super important point that it will just show up in everything we talk about. And you can get it formally from doing a saddle point expansion in the angle, or there are other ways to get it, but I'm not doing it. So what you are only left with is just the integral over omega. And I should get the right powers of omega here, just to make sure. It's omega, sorry, omega d omega, e to the I omega. So what happens is that now my x is in the direction of n, so I can just write this as a function of the distance r, because they are parallel, right? And okay, there's a minus sign there, hopefully. And so I get t minus r. Okay, and this, let me just write it here. It's the saddle approximation. Okay, and then you get j omega omega k, sorry, omega x. And then there is a conjugate term, I minus omega t. Sorry, minus omega okay. Hopefully that's it. Okay, so this is my radiative field as I go to infinity, to non-infinity. And you can check it depends only on this combination, which is usually referred to as the retarded time. And this one usually as the advanced time. Okay. So let me just make one point here. The point is what would happen if I had a j that was a static source? So what would happen if I take j omega equals delta omega? Okay, why is this interesting? Well, j omega having a delta means that it only has 0 modes, right? So it's static. And so static potentials are our favorite potentials. This is like the Coulomb potential, right? The thing that actually kills this, this charge. So what happens here with this static potential? So phi radiative of the static potential, right, is a 0. And that 0 comes all the way back from our sign. This sign of k0 tells me that we are dealing with a function that's close to k going to 0. It's odd. So it's going to kill whatever contribution looks like the 0 mode. And these 0 modes are this Coulomb potential, right? So this radiative field is killing the Coulomb field. It's defining something at non-infinity that agrees with my retarded field at non-infinity, but it doesn't have a Coulomb component. So that means that this retarded field at non-infinity doesn't have a Coulomb mode. And that's the perspective that Coulomb fields actually go to space like infinity. So I can even make it a little more precise. Maybe I'll refer you to one of my papers, but I guess I can say this J, okay, I'm going to get into trouble here, but I'm going to try to make it precise. This J can be interpreted as the classical limit of a creation operator where my expectation is taken over some state, okay? So this is what goes back to the idea of waveform. And this is going to be an out state, so actually I have to conjugate it just to evolve it to the infinite future where we are looking at the operator. I have to conjugate it with the evolution operator. Okay, so this is actually what we discussed yesterday. These waveforms are there. And what I do is that I compute the expectation value is a one-point function. And I take the classical limit as I briefly mentioned. So in the case of psi being one particular state, so if you imagine psi being a one particular state, okay, if psi is a one particular state with a wave function and all that, not the two particular states, just one example, then this will become, you can check that psi, that J exactly becomes, J becomes delta function of P, the P where this is localized. So this is localized around a big P. It becomes a delta function of big P dot K, which is exactly K0 in the reference frame of P. Is this delta omega. Okay, so for a one particular state, for a one particle amplitude, if I want to call it like that, I don't really have a radiative field. And this goes to a fact that Henrik and David mentioned, which is the fact that these three-point amplitudes don't really live in the Lorentzian signature because they involve radiation. And there's no radiation for a one particle state. Right? You need to accelerate it with something external. So these ones don't give you anything here. The amplitude is 0, which is exactly the statement that these three-point amplitudes vanish in 3,1. They do not vanish in Kleinian signature, so I spent some time working on that, in which case, actually, the Coulomb modes are contained in this function. But we are in the Lorentzian world now, so we cannot say that. And you can imagine that the way to fix this is just adding another state so that essentially these particles can accelerate and can radiate, right? That's the way that we were discussing with a different wave function, blah, blah. Okay. So that's exactly what we're going to say next. So these one particle states are not radiative, but if I put two particles here and two particles here, then I have a non-zero J, and so I have a radiative field. Someone asked yesterday, how do we know that this calculation is in? It's not obvious. I mean, I did think a little bit more, but it's not super obvious without doing the actual calculation. The only thing I can say is that now when we compute these operators, we are not time ordering, right? We are not time ordering. We are putting S dagger first before A dagger and before S. So the fact that we have an ordering that's not the time ordering of the Feynman propagator tells us that it's better to use the Schwinger-Keldysh contour. So that's roughly what I tried to explain in the previous case. Okay. So let me just what should I say? So, okay, I show you that this phi is a solution of the free wave equation, right? So what? So there are many ways to tell this story, but essentially, this phi generates a force, right? So now I'm going back to this problem. The phi radiative generates a force. That force doesn't have a Coulomb mode, so it doesn't diverge, right? And so, you can imagine that for a scalar theory, well, for any theory with a massless particle, there is a field strength which is the derivative of this guy. So this is what's gonna accelerate my electron, and it's gonna be smooth as I come close to it. Okay. This force itself is what people sometimes refer to as ALD, Abram-Lorentz-Dirac force, or self force, whatever. Same thing. And in the scalar case, it's just a gradient. So I'm going to discuss this toy model tomorrow, and we're going to discuss self force more in detail. But I just want to leave you this sort of answer of this problem. Now, you may have puzzles because this actually solves the free wave equation. So how does it even know? Like, so this is a vacuum solution. How does it even know that there's an electron here? Right? It's just a free solution. Well, the answer is because we showed that this guy coincides with our actual field at null infinity. So it knows there is an electron, just because it knows the boundary condition. So that's how it's sourced. At the end of the day, it's sourced by the electron in a way that Dirac famously worked out. Is there any question about that before I jump into this ugly formula that it's going to take the whole thing? Yes. Yeah. Yeah, that's usually called the Coulomb piece. Yeah. Inside, yeah. Yeah. Yeah, so I plan to discuss that tomorrow. But yeah, I mean, Ricardo would say there's some tail terms. I mean, there are many ways of doing it. Yeah, it's a very nonlinear effect. Yeah, and I mean, and someone wrote the formula, so I will give you the formula, but it's very nonlinear. Yeah, yeah. But all of this will be there, right? So all of this retarded story, radiation, field, it's all there. You have to add just one more thing, which is this other component, but the story is more or less the same. Yes. Okay, so let's just go back to this. Sorry, I said ugly formula, but maybe David will watch it's very beautiful formula, David Kosover. This is called the KMO. Sorry, it's just long to write, but it's very, very beautiful. And actually, I will explain why it's beautiful. So I messed up yesterday. I mean, I tried to make it nice, but you have to make some definitions to even write it, right? So I have to define this phase space measure. So this allows me to just integrate particles one by one. So I'm looking at just the case in which we exchange one massless particle. So in principle, you can exchange more than one massless particle, right? Let me call it whatever, R3 and R4, right? And I just have to keep integrating over R3 and R4, right? Just integrate over them. So if you don't recognize this formula, it's because I changed a little bit the notation, but it's essentially what I call I2 in the lecture yesterday. It's I2 mu. Except that in I2 mu, we were computing the deflection of one momenta, which is P1. So we were looking at P1 minus R1. Someone asked also why there is not many more massive particles, we are only increasing our massless particles. It's because you cannot generate more massive states, right? There is no way to create a new black hole in this in this game, even though it should be there. So actually, I leave you with that sort of puzzle, how to make this into a merger, where you take two black holes and you get one out of that. This one actually has 2 going to 2, and then you just have extra radiation. And then you sum over all possible states, right? So all possible radiative states, but then you look at the momentum of one of them, right? So we want to look at the momentum of this state K. And the good thing is that I wrote it in this way to just make the point that this is a perfect square, right? That's interesting, the fact that this is a perfect square. It wasn't obvious for the calculation. I remind you that we had a term that looked like psi, t dagger, p1, t psi. But now I'm changing this p1 by k, right? Well, obviously p1 plus, well, there is a conservation of momentum here, but I'm just going to look at k, which is the radiative momentum. So now I have a perfect square. Let me just make it a little more precise. I'm going to call this, so these are smearing wave functions, so I have p1 and p2 integrated over these wave functions. I just call this psi. I scatter, let me just go from the left to the right. I scatter this psi with some S matrix, right? This is my S matrix. And then I check what happens on the other side by measuring, essentially measuring a graviton of momentum k. This joke is not working. Okay. I have a graviton of momentum k. Sorry. And then I have another 2 particular states. Let's just look at the simplest case where I don't have anything else. So I have R1 and R2 are just some other massive states. And then all I did is to square this, right? So I have something that looks like R1 and R2 on the other side. Now I have an A dagger. Now I have an S dagger, just because I square it, and then psi. So I mod square it, right? And there are many, many things we can say here. So the one thing maybe I want to stress is that if we sum over all R's, I'm here truncating to 2 R's, but we can sum over all of them, then this will become a completeness relation, and I will have something that looks like A dagger K, AK, with the same momenta, right? And then I just take the expectation in this S dagger side, right? So that's interesting because this is a 2-point function of gravitons. It's order, right? It's not time order. It's putting one before the other. So it's like the Whitman function we were looking at that I erased. The Whitman function has an order. So we're computing this Whitman function. But then we have an integral. If I sum over all of these R's, then I forget about this integral, but I still keep my integral in the phase space K. And then I keep K mu, right? And that I claim is the radiative momentum. It's the momenta radiated by the graviton. And now it's obvious because essentially all I'm doing is I'm looking at this expectation value of my number operator. This is counting how many gravitons I have, right? This is just a number operator at a particular position in the phase space. And I just count how many gravitons I have I multiply it by the energy of each of them. And that gives me the momentum of all of them. So as an exercise or homework, which I think is like the hardest one so far, even that one is easier, maybe you can show that the radiative momenta, the time derivative of this, equals k dot 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 ij k dot 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 ij. Okay, this is something that should follow from this formula, but it's not. So obviously, what I'm doing here is I'm sorry. This is a scale. I mean, this is more like a scalar theory, but the idea is the same. This is a radiative formula that Ricardo showed. And to recover it, all you need to know is you need to take this momentum integral into time integral, into space integral. And that is doable by first showing maybe that this is the integral over the integral of T0 mu, right, T0 mu, 0 x. So actually, this is the stress energy tensor, which has one derivative. That's the derivative here, and it's quadratic in the fields. That's this. And then you can evaluate at time, if you want, you can evaluate at time infinity minus infinity. You need to subtract the energy flux to get that formula. And then if you shuffle, if you massage this T into a Q, then you can show that that's the radiative component. Yeah, I'm sorry, this chart is not as good as I thought. Okay, so that's one observation. It's satisfying to at least understand how the radiation came about. The other interesting part is that you can sort of convince yourself that this is related to that, to these waveforms. And at least in the leading order, it's sort of obvious. Probably write it here. So if you want, this is something that you can show as well, which is the fact that at leading order, you can imagine that R1, R2, R1, R2A, S, psi can be approximated by psi, A dagger, psi. A dagger, sorry. I may be looking at the other. This has two components, so maybe I should be looking at this one. Yeah. So this is the waveform, right? Okay. And this is maybe we can call it the radiation kernel. So this is just to say that the waveform is just a way of estimating how many gravitons there are in some direction. Obviously, it's the same thing that we need to compute to get the momentum. And to show this is just the fact that, well, R1, R2 are really very close to psi, right? So they are essentially very slightly deviated from psi because you are, again, you're taking this classical limit where the outgoing momenta has a little deflection. So this is essentially psi. And then the other thing you have to notice is that you can approximate this by 1. The exact formula is 1 minus I T dagger. But then you can show that T dagger essentially doesn't contribute at leading order, right? So these formulas at leading order in G are the same, which is satisfying because we are looking at these waveforms. And so we want to know what the radiation coming out of them is. How much time do I have? Half an hour, okay. One more thing before I jump into a final topic. Let me just make even more remarks about this puzzle, which is the starting point, is related to that other formula, because what we're doing here is we are emitting this extra state, right? We call it A dagger K, maybe, or AK. And then we are reabsorbing it, right? That's what the square of the amplitude means, right? So if this was a binary, I mean, if this was Ricardo, right, you would imagine that this two-particle state is a binding, is a binded whatever binary, and then you emit this radiation modes, I think he calls it, and then you reabsorb them, right? That's what the squaring means. We're squaring this. We're squaring it along the cut, and we're cutting because it's radiation. That's the meaning of the fact that we have to integrate our on-shell particles, right? So this goes back to my electron puzzle, because now what my electron is doing, if I were to draw a word line, it's emitting these modes. So I have the Coulomb modes, and I have the radiation modes. The radiation modes are the ones that sort of squeeze the field lines. I throw away the Coulomb modes by defining this radiative force, and then I act with the radiative force on the momentum of the electron. All right, so that's what accelerates my electron, and this is the ALD Abraham-Lorentz-Dirac force. And tomorrow we will discuss radiation reaction in gravity, if I have the time. Okay. So, okay, now we will jump into the actual topic that I want to cover first, which is the wave equations. Okay, so now we know how to compute retarded propagators, and we know how to compute radiative propagators, right? And so we want to relate that with amplitudes. So we want to compute an amplitude using this technology. So the first thing to understand is, this flat space discussion has an analog in curved space-time. So these are curved space-time, but I'm going to insist with my scalar toy model. I'm just going to make it curved. Okay, that's just going to simplify the notation. Very rarely it affects anything, but let's just discuss the scalar toy model. So now I have G mu nu, whatever, D mu. The first one is covariant. The second one doesn't need to be covariant because it's a scalar. Okay, and now you can either. So here it comes the fun part. Instead of having this stress energy tensor, we're going to have a source, right? So you may imagine, so what is this source? So we need the source to discuss all of these amplitudes because they are the on-shell modes, right? So what is this source? So the source will be, I'm going to imagine that, I'm trying to understand this self-force problem, right? So I'm going to imagine that I have a big black hole, and then what I'm going to have is a point particle, right? Something that maybe some people will call the extreme mass ratio situation, extreme mass ratio in spiral, right? So I have a point particle. It's point particle, but it's not neglectable, right? So the point particle itself has a stress energy tensor, T mu nu, which I represent in this toy model as a J. And what's going to happen is that it's going to source. So the black hole is sourcing some metric. But then the point particle itself is sourcing a stress energy tensor. So it deforms the metric in a particular way by some linearized field, right? So that's usually called the linearized field, right? And it grows with the order of mass, with the order of the mass of the particle, or the mass ratio if you want. So this linearized field, I'm going to represent by phi. And this stress energy tensor, I'm going to represent by J. Right? So that's the problem I want to solve. I want to really back react on my black hole. And then once I solve, again, same thing. Once I solve this linearized field, I can imagine how it's going to shift the trajectory of the particle itself. And then there will be some deflection. Okay? So that will be tomorrow. Today we're going to understand what's going on here. Okay, so what we do, if we have spherical symmetry, hopefully we can assume that for now. So we need some symmetries. If we don't have symmetries, we are done. So we can do it in Schwarzschild, we can do it in Kerr, But if we don't start from a background that we understand and deform it, we are done, unless you use something like effective one body, which I don't understand, but in that case, somehow you can still have some symmetries, okay? But here we are thinking of a very small particle deflecting around a big black hole, which is Schwarzschild, okay? So in that case, we can just say, okay, it's going to have some spherical symmetry and some time symmetry. It's a stationary solution. And every time you have spherical symmetry, the representation of that is given by the spherical harmonics. And so you have these things. And so you have a field that looks like this. Right? Where we technically need to also integrate over omega. But I'm going to do something a little tricky, which is I'm going to look at just one mode. And this is motivated by the formula I wrote first, which I think is the most important formula of this lecture, which is the fact that asymptotically, this radiative field is a function of my retarded time. I'm just looking at one component. Then there will be a complex conjugate, where I look at the 1/r term. And then all the Fourier transforms just reduce to a Fourier transform over the retarded time. And then this source is evaluated in this position. And so obviously, I forgot the factors here. But the important thing is that I can call this my amplitude field or my radiative field in my omega component, right? So this is what I'm looking at here. I'm looking at one of these components that eventually this will decay as 1/r, and it will become that source over there. Okay. But it's important to work in this frequency domain because we are not astrophysicists, right? So these guys do time domain, which is a mess, but we like, in physics, we like frequency. Okay, so let me just define this is standard R star, which is R plus 2m log R minus 2m. And I do this to deal with the redshift coming from this equation. There will be an FR. I'm not going to do that. Anyway, so this absorbs the redshift factor. So you get the second derivative once you plug that in of phi Lm. Let me just call it phi omega here. Then it's an omega squared term. Yes, the time derivative term. And then there is a potential, which I was about to write, but I was running late. I was running late this morning, so I didn't I didn't write. But it has something to do with L and M. You know, M being the frequency of these guys. If I was really pushed, I would say it's something that looks like L plus 1 over R cubed maybe times 1 minus 2 M R, I think. And then maybe there is a GMR. Yeah, sorry, I already messed. Yeah, it must be something like this. I'm not sure. I think there is something that looks like this. Yeah. It always vanishes at the horizon. That's the important point. Yeah, so it must be something that looks like this. It has an R squared. Okay, so these are phi here, and then there is my source, right? So now I have to expand this source in the spherical harmonics. So I'm just going to say it's going to be given by a function that looks like this times the stuff. Now, I would like that function to have some symmetry so that it's simple, and it will have, if this is a word line, almost a straight word line, then this function will be spherically symmetric in the SO3. So actually, it won't have, I think it won't have any M component. So for certain straight lines, this simplifies. Actually, I think here I already assume that M is, sorry, I'm looking at this spherical. Yeah. Yeah, but in general, there is an LM, of course. Okay, so now I have JLM. And that's my source. Okay, so the first observation is that this defines something that looks like a Schrodinger equation, and we know how to do it from quantum mechanics. The interesting thing, perhaps, is that the Schrodinger equation is defined on two boundaries as given by this map. So the map tells me there's a boundary at r goes to minus infinity, and there's a boundary at r goes to plus infinity, right? So one is the horizon, and the other one is the null infinity, right? Plus or minus. But it doesn't really care whether we choose plus or minus, right? It just cares about the fact that we are at infinity. So we have our, sorry, just to make it very precise. How much time do I have? 20 minutes? I thought this would take longer. Sorry guys. Maybe we'll wrap up, and then maybe we'll have questions, because yesterday we didn't have a discussion. So yeah. So I didn't prepare the next step. So let me just leave you guys with the following question. All right, it was really fast then. Okay. So the question for you is, what are the boundary conditions? What are the boundary conditions? The boundary conditions, right? At the horizon and at scribe plus. Okay, and how do you justify the boundary conditions? Okay, so it's a black hole, not a white hole, right? So there is something going on. Sorry, I messed up here. Yeah, we're looking at this patch, obviously. We don't care about what's happening beyond the horizon. I was doing Minkowski. So what's the boundary condition at the horizon? And what's the boundary condition at I plus? So that actually depends. So there are many answers to this question, whether we do a scattering. So sometimes we want to throw in something and then understand what comes out of it, right? So that looks more like a scattering. Some other times, we may want to understand what are the natural modes in which this thing oscillates, meaning there's a vacuum perturbation, and so we want to understand the frequencies of like the ring down or something. And so in some cases, there is nothing coming from here. There is only something sort of bouncing between the horizon. Sorry, I keep messing up with the something bouncing between the horizon and the scribe plus. So that something is called the quasi-normal modes, right? But these are different situations. We have quasi-normal modes and we have scattering. Interestingly, they are related. And hopefully I talked about that yesterday. So I think it's okay to wrap up here. We already discussed a lot. Is that okay? Yeah, good.
Okay, so we have plenty of time for questions. Who wants to start? Well, okay.
Can you derive the memory effect from this formalism that came?
Oh, that's very interesting. Yes, absolutely. Absolutely. And the idea is that, I mean, this formula has everything in it, right? So you just need to kind of mine everything out of it. Let me just say one thing which is interesting before I discuss memory effect. It's just the fact that, just from the picture, there is this radiation reaction force, right? And so we know that that's the thing that accelerates the particle or the binary. But it's the square of radiation, so that's actually a very interesting sort of version of what's called the optical theorem, right? This secretly this optical theorem that tells us essentially the imaginary part, which is dissipation, is the square of the cross section, right? Sorry, there is a cross section. What am I saying? Yeah, the imaginary part in the forward limit is the cross section, roughly. So what is this cross-section? Well, the cross-section is essentially how much we radiate. So we radiate momentum, we radiate angular momentum. So we radiate k mu, and we radiate j mu nu, and all of those things are related to this kernel. Just as I showed in this formula, the radiation of momentum is related to this amplitude square. So that's the cross-section. And then the imaginary part is essentially how much we lose to dissipation or so, and that's kind of the, it's related to the radiation reaction. So I don't have the formula actually prepared, but the idea is that we can match this K, yeah, we can match the radiative part to the self force. But maybe I'll do that computation tomorrow. Yeah, but yes, that's just to say that this amplitude has radiation of angular momentum, and so that can be related to delta P, right? So now imagine that we have delta P2, and then the radiative momentum, right? I call it K, right? So if I know the radiative momentum, then I know my momentum deflection. Okay, so now how to answer your question? Memory is something it's easier to look at in the waveform than in the momentum. So in the waveform, which is there's just one copy of this, right? So it's just this S dagger A, right? Which at leading order is just one copy of this. This amplitude itself has a soft theorem, right? Has a component that looks like, if I've ever read about these soft theorems, there's a component that factorizes into a 4-point amplitude, which is the conservative part, times a radiative 3-point amplitude. And so once we factorize, so once we expand at all orders in K, so 1 over omega, which is this pole, plus omega to the 0, which is something related to angular momentum and so on, then we can see the tower of memory effects, yeah, by looking at the waveform, yeah, and expand the amplitude. Yeah.
Cool, thanks.
Yes, and I did this calculation very long time ago, but then it recently resurfaced in the context of calculating angular momentum, which is really complicated from general relativity. So you need to go and look into these diagrams, and I believe it was done recently using the Stringer-Keldysh idea. So this is kind of a very interesting simplification.
Other questions? Okay, maybe I can ask one. Do you want to ask a question? You have your hand slightly raised. Okay.
You mentioned how going to other signatures would help for the Coulomb.
Sorry, can you repeat?
You mentioned how going to Kleinian signature could
help.
Yeah. Could you explain a bit more?
Yes, so Kleinian signature. Yeah, I erased it, but we were discussing how a single particle cannot radiate, right? A single particle, it's already generating only Coulomb modes, is stationary. And that has to do, it's very closely related to the propagators having this I epsilon prescription, right? So in one case, we have K plus square minus K0 plus I epsilon square. Right? This is something I can only do in Lorentz signature because I have time. In Kleinian signature, I actually don't have an I epsilon prescription, and that amounts to the fact that it's very much like this thermal system where the retarded green function and the Weidmann function coincide. There's no definition of the retarded green function. All that you can do, which is Lorentz invariant, is this. And if you do that, you can compute both the amplitude, that looks something like this, and and the Coulomb field from it. So both of them come from this propagator. So you can compute the 1 over r potential from this propagator and also the amplitude from the radiative potential because they are the same. I should say that the reason for this I epsilon to not be defined as in the Lorentzian case is that in Kleinian signature you can essentially do parity, but doing it as a continuous transformation. So you can rotate t to minus t by a Lorentz transformation. So it doesn't have any meaning to put k0 plus I epsilon because we can take k0 to minus k0. It's just a Lorentz transformation. So there's nothing like retarded or advanced. Yeah, that's the peculiarity. The light cone, future and past is connected in Kleinian signature. Yeah.
Any other question? Okay.
Yes.
Here you're working with the radiative graviton, right?
Yeah.
So my question is like, in which process of the whole merging does all of this work? Like the merging in the quasi-normal part, on the tail, or you can compute every part of the whole scattering process of black holes?
Yeah, that's an interesting question, and I think it's something that people are still trying to answer. So there are many sort of developments towards applying to the merger, which I have to admit I haven't really followed many of them. But the original idea at some point was that this so we're dealing with the scattering situation first, right? And once you understand scattering, you understand how to resum the diagrams, right? You're resumming all of these G squared, G cubed, and so on, all of these like post-Minkowskian terms. So if you understand how to resum the diagrams, you may apply that to any other situation in which you need to deal with essentially the same diagrams. Now, there are things that tell you, well, it's not exactly like that because there's no log times effects in the binary. We don't know those show up, at least I don't know how they show up in the scattering situation. So the map from one answer to the other answer is complicated. You would like to have an analytic continuation, and we have that in the conserved case, thanks to Porto, which maybe he's watching, and Kalin. So they did the whole analytic continuation for just the conservative part, which is the term that I didn't write. But you can take essentially the elliptical trajectory into a hyperbolic one. So that is done. The radiative part is also involved in this non-Lagrangian time tail, whatever. It's not clear if you can continue one into the other. So that's kind of the whole. It's a kind of a pressing problem. Okay, you're bringing up some of an important point here that obviously I'm not discussing. But let me just say that this is not only very cool, but you can apply it in all situations where you have a source and a field in curved space. So it doesn't have to do, I'm kind of recycling the calculation, right? So I did this calculation in Teukowski equation. What's the point of it? Well, sometimes we want to understand quasi-normal modes. Some other times we want to understand photon rings, resonances, accretion, So we recycle this thing over and over. It's important to know how to deal with it. And we can deal with it in care. So it applies to many contexts. Like love numbers, for instance, is a different situation where we can compute the running of love numbers from these quantum amplitudes, which I worked on, but I didn't have too much chance to talk about. But these are the amplitudes where you have two massive particles and two gravitons. So you can imagine it's a solution of this scattering problem, like coming from here and then scattering back to infinity. So that doesn't need to relate to the binary spiral, but it relates to love numbers or quasi-normal modes and other stuff. Yeah.
Anyone else? Okay, if not, let's thank Alfredo again. And we should be back at 11.